thank you so much for inviting me. So I'm going to be talking about detecting non-permutative elements in K1 of varieties using point counting, but the main issue for a lot of people is that the term non-permutative in K1 of varieties are generally not terms that people know. So the first part of my talk is going to be explaining the title of my talk. And then I'm going to talk about how one actually does this. So the growth and decaying of varieties, K0 varieties, and there's some base field or maybe a base scheme, but whatever. I'm only really worried about fields. I'm only going to be worrying about finite fields even. So for almost everything that I say, you can assume that I'm working over a finite field. This is the free abelian group generated by varieties over K, modulo the relation that if you have a closed immersion y in, not in y, in x, then we have that x is y plus the complement. So when I say variety, I don't mean smooth, I don't mean projective, I just mean reduced separated scheme of finite type. Or if you want the bunch of places where some equations are zero and some equations are non-zero in some kind of nice model. And this ring is, so this is a ring, so it has a ring structure where we represent multiplication by the Cartesian product. So this is a natural sort of algebraic structure to classify the cutting and pasting of varieties. If two varieties are related by a series of cutting and pasting relations where you can cut out a subvariety and then glue it in a different way, and then maybe cut out a different subvariety and glue it in a different way, or maybe cut a bunch of things out and then glue them all back together in a different way, all of these things are going to be equal in this ring. Now, the converse isn't necessarily true. In fact, the question of if two varieties are equal, what do we know about them? This is a really difficult question, and there's a lot of stuff we don't know. So this is a really complicated, interesting ring. It appears because this is the universal additive invariant on varieties, in the sense that if you have a map from varieties to some abelian group A satisfying this relation, so then so for you have, if we call this mu, as it is usually called, mu of x is mu of y plus mu of the complement, then this factors through the growth and decaying. So this is unique. And if mu is multiplicative, so if mu of x times y is mu of x times mu of y, then this will be a ring homomorphism. So if A was originally a ring as well, and it satisfies, then this will be a ring homomorphism. So this sort of, if we could understand the structure of the growth and decaying of varieties, we could understand all such additive invariants. So some examples of these additive invariants, just to demonstrate that this is actually an interesting thing to study, it's point counting. Point counting. If K is finite. So we let A be Z, and to each variety we assign the number of K points, and then it's clearly additive because if you have a closed immersion, every point is either in the subvariety or in the complement, and so this works and we're all happy. Another example, and this is going to be pretty much the only example when K is the complex numbers, we can set A to be the growth indie group of mixed Hodge structures. And we can map a variety X to its mixed Hodge structure. This is a structure on its cohomology. And you do this really by taking the alternating sum of the class of the ith cohomology. Each of these has a Hodge structure. Oh, that's not the sum. I wanted the alternating sum. And this will, this is another such invariant. The fact that it is additive reflects the fact that mixed Hodge structures have a long exact sequence for these kinds of splittings. And so this is really, and this is really an additive invariant. And the last example I want to give is the local zeta function. So in this case, we set A to be, again, we're working over a finite field. So we're going to set A to be 1 plus TZ T. So these are power series in T that start with a 1 under multiplication. And we are going to map X to the following function. So this is X times the sum n bigger than or equal to 1 of the number of points over FQ to the n. Oh, I'm assuming K is FQ here. So we take an n degree extension, we divide by n, and we multiply by t to the n. And so this counts, this is sort of the number of points over all possible extensions, well, finite extensions of your finite field. And the theorem is this is an additive invariant, and in fact, this group has a ring structure on it that actually makes it a multiplicative invariant. So somehow this growth and decreasing of varieties contains the information of all of these different kinds of things, which is one indication of why it's so difficult to study. Now, I'm not an algebraic geometer or a number theorist. I'm a homotopy theorist, really. And so I look at this 0 and I go, that shouldn't be a 0. That should really be, a space or a spectrum, and it should be, it's homotopy groups. And I'm not going to talk about the details of this in this talk, but in fact, there exists a spectrum, K of varieties, such that, so this pi 0 is exactly K0. And the higher homotopy groups encode other geometric information. So it's not just an Eilenberg-MacLane spectrum. I mean, clearly you want K0 to be anything, I can make it be anything. But no, this actually has, there's an actually geometrically significant such spectrum. And you can construct it just using various techniques in K-theory. You can make a Waldhausen category that encodes this information. You can make a gamma space that encodes this information. I'm not really going to go into the details of that. I'm just going to say it works. There's various standard constructions in K-theory that let you do this. What I want to talk about is what could these higher homotopy groups mean? What is this other geometric information, and how can we find it? So I want to talk a little bit about K1 in general. I'm not going to talk about anything higher than K1 because I don't know what anything higher than K1 means for this spectrum. I would love to know. I think it would be really cool, but I don't. But I know a little bit about K1. So, theorem. So K1 of varieties is generated by the following. You take a variety X and you take a decomposition of this into pieces, into finitely many pieces, X1, Xn, and you take two different piecewise isomorphisms. So really what this is it's two different ways of splitting X up into the same pieces. So this is sort of a scissors automorphism. So you decompose X into pieces and you reassemble it. And when you add these, you can either take disjoint unions of varieties, or if it's, you can also refine them, any kind of basic thing that you can imagine you should be able to do with this information, you can. And this is an abelian group generated by these. If the two different ways of assembling it are the same, it's the trivial element. If you take such a scissors automorphism and you refine it, meaning just cut up the pieces but have them assemble in the same way, it's the same element. If you take two of these and compose them, it's the sum. So it's really, it works the way you feel like it ought to work. I suppose I should put that this is my theorem, but these kinds of piecewise automorphisms are really difficult to work with because they're a really complicated kind of thing. So we might want to be able to say, okay, well, we should be able to do some kind of better object. I mean, again, if somebody else has an idea, I would love to discuss it, but I have no idea how one would even work with a bunch of piecewise automorphisms. Like if I wanted to try to analyze the group of piecewise automorphisms, I have no idea how I would do that, really. So attacking this as just the entire thing, because this is for all varieties. So you have one of these for every variety X, and it's so enormous, I wouldn't even really know how to deal with it. There's a couple of other things you could try to do. So observation, any automorphism is a piecewise automorphism. I mean, there's no reason why you have to break it up into pieces. You could just say, okay, we have an X, and one of our piecewise automorphisms is going to be the identity, and one of them is going to be some other automorphism tau. That's a perfectly reasonable thing to do. And so you can try to see what kinds of elements in K1 you can pick out with these. And just purely doing this, I tried doing it, but I couldn't actually figure out a way to do very much without also adding a second part that I'm going to say in a second. I will mention there is, for any variety, so for any X, there is a homomorphism from the automorphisms of X into K1 of varieties, mapping it to this, every automorphism to this kind of element that I drew here. So you could do this purely if you could somehow analyze it directly, but I don't know of a way. I haven't been able to come up with anything along those lines. But you can also do the following. If an additive invariant extends to a spectrum, so if instead of mapping from just K0 to some abelian group, if we map from K to some spectrum X, I shouldn't call it X because I've been calling varieties X. What are spectra called other than X? I don't know. I'll call it A. If there's a spectrum map like that, then it induces a map K1 of varieties to pi1 of A. And so this is sort of a higher motivic measure, and because you can use motivic measures, additive invariants, I've been calling them additive invariants. They're also called motivic measures. Because you can use additive invariants to study K0 varieties, there's no reason why you couldn't use additive invariants to also study K1 of varieties. So a couple of examples of this kind of thing. So point counting, which I already mentioned on K0, it in fact extends to a map from K of varieties to the sphere spectrum. And the reason it's the sphere spectrum is because the map that you are actually looking at is the map from varieties to finite sets, sending any variety to its points. And the K-theory of finite sets is the sphere spectrum. And we also have a map back because we have a map from finite sets into varieties just for any finite set taking a disjoint union of points. And you can see that if you go around this way, This is the identity. And so what this means is that K1 of varieties has a direct summand, which is Z mod 2. We usually call the other bit the reduced part, because this is sort of naturally the pointed part, which is the less interesting part of the K-theory. The way that you often reduce K-theory by taking out the free modules, this is the same thing, only you're taking out the pi1 part of free modules. So this is K1. And so then, there's a natural question of, okay, for the case of finite fields, is this 0? And it turns out that in general, it doesn't have to be 0. So if K is FQ and Q is 3 mod 4, K1 reduced is non-zero. And the way that you can do this is just by looking at the following element, which comes from one of these automorphisms. We have, if we take 2 copies of the projective, oh, nope, I am lying. If you take the projective plane, the projective line, and you take the automorphism, which is x maps to 1 over x, this is non-zero and not equal to the element that you get by taking 2 points and then swapping them. Oh. Which is the element that represents the non-zero element in this Z mod 2. It's just the swap. And so you can construct this when Q is 3 mod 4, and it works. But only being able to do it when Q is 3 mod 4 is a little bit frustrating. And also, there's this other sort of observation, which is the following. So I'm going to cite Jonathan for this. So,
hey, Ina, sorry to interrupt. What happens when Q is 1 mod 4? Is that they're the two automorphisms are there become equal?
It's unclear. I mean, it's clear they're both there, but we couldn't prove that they're not equal. We couldn't prove that they are equal. In fact, I'm pretty sure they probably aren't. But we couldn't prove that they are not equal using the. It's terrible when you have to have multiple negatives, but you can't actually cancel them out. We couldn't prove that they aren't equal using the technique that we had. Okay, so there's a question in the chat that I'm about to hopefully answer. So there was a question in the chat that I'm just going to be repeating. So K-var is an E-infinity ring spectrum. And the question I had mentioned before, but yes, the map from S to K-var is the unit. So this is sort of actually I'm now worrying about, but yeah, anyway, I'm not going to say this because I'm now worrying about a technical issue. But anyway, I'm going to ignore that. So K of R is an E-infinity ring spectrum. And what this means is that the homotopic groups are a ring. And so we have the following multiplication. We can take K of R times pi 1 of S, and we can multiply this, and we're going to get an element in K1 of varieties. And what this does on representatives is it takes, if we take X and eta, we're going to map this to the element where we have 2 copies of X, and then we swap them. And just a totally reasonable thing to do. I will quickly mention, so in general, we get a map from K0 varieties tensor, the nth stable homotopic group, and this is going to map to Kn of varieties. And you can use this to show that when the base field is, I think, C, and I didn't actually check this. I think you need algebraically closed, but not much else. Algebraically closed in characteristic 0 and not much else. So when K is C, there are infinitely many non-zero groups. But actually computing the higher ones becomes much more difficult. So I just want to say this as an aside and then ignore it. But in particular, there are these elements. And these elements are also kind of boring. They aren't actually capturing any new information about anything, any of the interesting geometry inside X. It's just, oh, look, I can treat X as though it were a point and move it around as though it were a point. There's nothing deep going on here. So these are called permutative elements. So you have the permutative elements inside K1 of varieties. And the question is, and the question that I want to talk about is, do non-permutative elements exist? Now, in order to detect this, what you want, so what we need is an additive invariant on K1 of varieties, which distinguishes between permutative and non-permutative elements. And one of the hard parts of that is a permutative element is determined in terms of the ring structure. So if you want an invariant which can detect it easily, what you really want is a ring morphism out of the homotopy groups of the K-theory varieties. And so ideally what you'd like is an E-infinity map on K-theory, which is really hard to construct. And surprisingly frustrating, because it feels like these are the kinds of things we should be able to just do. And in particular, by the way, if anybody knows of a place where this is just written up and I can cite it and don't have to write up all the details myself, I would be deeply grateful. And this is a proof from Donald Yao, which says the following: given a map, given a functor C to D between bipermutative categories which is strict additively and lax multiplicatively, there is an induced map from the K-theory. Well, there's an induced, I'll do it. So what's going on? Sorry, there's an induced ring homomorphism K star of C to K star of D. And in particular, the actual statement homotopically is that the induced map on K-theory is simplicially homotopic to an E-infinity map. But I don't actually know that it is an E-infinity map. And something similar about being able to construct an E-infinity map would be great, but I couldn't actually do it. So if somebody who is much more technically competent than I am, or even somewhat more technically competent than I am, had an idea about how to do this, I would be thrilled. But this is sort of the key point, that the way that these kinds of, this is sort of the key technical point of being able to construct this. So now that the key technical point is out of the way, I'm going to tell you about how to actually construct this additive invariant that lets you distinguish between permutative and non-permutative elements. So here's how we're going to do that. Actually, so first I need one more definition. I'm going to actually write this one as a definition. An almost finite set S is a z-hat set. So just, I don't know how many people work with profinite groups. This is the profinite completion of Z. So it's the limit of all of the Z mod ends. So it's the analog of the p-adics where you don't restrict yourself to a single prime and work with all n instead. So it's a z-hat set such that S to the H is finite for all H. So these are nice subgroups. These are nice subgroups of z-hat. And so what this says is sort of there's sort of finitely many points at every level, and every point has a finite z-hat orbit. So what this says is you have z-hat acting on a set, and you sort of have at every sort of stage, you only have finitely many points that are being added, and then there's nothing up at infinity. You only have the finite portions of yourself.
Should there be a condition on H?
Yeah, whatever. H is closed or open or whatever. Nice subgroup. The ones you care about. Yeah, I mean, it's not the identity. Thank you. So right, so the canonical example of this is if X is a variety over FQ, then X of FQ bar is almost finite. And the key point here is that Z-hat is the Galois group of FQ bar over FQ. But these conditions exactly say, you know, what is X of FQ bar? It's all of the points over finite extensions. And because a finite extension still has finitely many points, each of those will have finitely many points. So you add finitely many points at every level, and there's nothing off at infinity. There's no point which is somehow fundamentally over FQ and not over, or FQ bar and not over a finite extension, because that's not how FQ bar works. There's nothing like transcendental going on in there. So this is the extension of point counting. Before we were just counting the points over the base fields. Now we want to count the points over all extensions. And unless your variety is very boring, there's going to be infinitely many of them. So we don't want to say, oh, like there's just infinitely many. We want to count how many there are at every level. And so what you get just by, you know, checking whatever k-theoretic structure you're trying to use, you get, if you take the functor, you take varieties, and you map this to almost finite sets, given by X maps to X of K bar, this induces a ring homomorphism. From the K of varieties to K of almost finite sets. So a couple of remarks here about sort of how this works and various annoying things that crop up that folks might be interested in. Again, I'd really like this to say that this is an E-infinity map. And naively, if you do this sort of the most general way, you need a theorem analogous to the one up here that I put, the one up here, where you want to say that, oh, you get an E-infinity map. And in order to do that with the sort of the things that are written up nicely in the literature, the best result I could find is Elmendorf-Mendel, which says that if you have a map which is lax additively and strict multiplicatively, then you get an E-infinity map. And at that point, I'm like, okay, well, what I need is a strictly associative product of varieties. And I was sitting down and trying to construct it, and I was having various issues because, you know, generally you don't worry about strict associativity. Things working up to isomorphism works perfectly well. And I just want to quickly tell a story because I thought it was funny. I was talking to some number theorists, and I was like, is there a strictly associative model of the fiber product of varieties? And they said, Ina, don't you know any category theory? You don't need to work strictly. You can just work up to natural isomorphism because it's a unique natural isomorphism. And I was like, it turns out that sometimes that's not good enough. And so anyway, it is possible to do it, but it's so annoyingly technical that I decided I would rather stick with this theorem I have the pink arrow pointing to. But I am finding it vaguely unsatisfactory. So I wanted to mention that in case anybody has better things than that. Okay.
Sorry, can I just ask briefly about that theorem? You're taking K theory of a bi-permutative category. That just means like group completion type of thing. Or
yeah,
like direct sum.
like a Siegel construction.
Okay. And you haven't, I mean, is var one of those?
var is not one of those, but this is one of the things I was sort of glossing over because that would take, like, discussing it properly would take the whole talk, and that wasn't what I wanted to talk about. But there is a construction of the K theory of varieties, which constructs sort of a helper category, which is bipermutative.
Okay, but it's like subtractive, or I forget what the word you use is.
No,
like that.
you don't want the subtractive version. What you want is these. If you take the assembler, everything here is with the assembler models. So subtractive categories and Waldhausen categories don't form symmetric monoidal categories, but the category of assemblers is a symmetric monoidal category. And you can show that both var and almost finite sets are monoids in the category of assemblers, and that this map is a map of monoids, and which is lax, which is right. And so if you have a strict map of monoids, then everything works and you're happy. But if you have a lax map of monoids, which is what you sort of get naturally, you end up with annoyingness. And that was sort of where all these annoying E-infinity issues started coming in.
Okay, cool, thank you.
That was probably more annoying technical things about E-infinity stuff than folks were interested in. But okay, so right. So if we're trying to construct this, we get this ring homomorphism, and now we're trying to do something with it. So we'd really like to know something more about this thing here. Now, I'm only going to call this a proposition because I don't think that this is terribly interesting, but there is a map from K of almost finite sets to the wedge over all n of the pointed suspension spectrum of B Z mod n. And I'm just going to add a quick conjecture because I'm pretty sure this is an equivalence. But just as a quick note about how this works, you can show that K theory, that you can show that at least as an assembler, almost finite sets is equivalent to the wedge as assemblers of these are assemblers generally that are called CZ mod n. These are as assemblers. And the K theory of this assembler CZ mod n is exactly this pointed suspension spectrum. And the issue is that it's known for nice Waldhausen categories, in particular Waldhausen categories with a cylinder functor, that K theory commutes with infinite products. But the Waldhausen categories you get from assemblers do not have cylinder functors. And I could not find an adequate or figure out an adequate proof that K theory would commute with the infinite product there. Actually, sorry, this is not as a wedge. This is as a product. Why did I write wedges? I'm too used to writing wedges. I apologize. These are products, not wedges. I'm lying. So this is true as assemblers. And so what you'd really like is that the K theory commutes with products for assemblers as well. There's no reason to assume that it doesn't, because it does for exact categories and it does for nice Waldhausen categories. So morally speaking, it should for everything. But I don't know of a proof. Regardless, all we need is that we have this map. So now we get a map from K1 of almost finite sets to the product of Z mod 2 plus Z mod n. And this Z mod 2 is the permutation component. And this Z mod n comes from the, well, it comes, I'm across 2 pages, but it comes from there. And so you get this map and you can actually compute what this looks like on permutative elements versus non-permutative elements, because this map is a ring, well, not quite a ring homomorphism, but ring homomorphism enough that you can figure out what happens to permutative elements. And the theorem is that the image, oh, sorry, and this one is called the internal. This is the internal variable. The image of any permutative element has all internal coordinates 0 when n is bigger than 1. So what does this mean? Like, what is actually going on? What's happening is that this K theory of almost finite sets, this splits every almost finite set as a disjoint union of orbits under Z hat. Each orbit of every element under Z hat is finite, so it just looks like a circle of Z mod n of some size that's being rotated by Z hat. So you have this set, and an automorphism of that set, a piecewise automorphism of a set, by the way, is just an automorphism of the set because the set has no structure other than its elements. And so an automorphism of the set rearranges some of these orbits and then rotates some of them. So the permutation coordinate counts the sign of this permutation of moving the orbits around. And the internal element measures how far, all totaled, all of the orbits have been rotated. Now, all that a permutative element does is it takes a bunch of orbits and it swaps them around and it doesn't rotate anything. And so it can't produce a non-zero internal coordinate. However, a different automorphism could rotate elements. And so it could produce a non-zero internal coordinate. So now, in order to demonstrate that there are non-permutative elements, and or even to identify that a particular element is non-permutative, you need to compute its image under this map and compute its internal coordinate. And if it's non-zero, then it must be non-permutative. Okay. So the goal now in the last 5 minutes is to construct one of these elements. So I want to give a couple of explicit examples. So the first one is just going to be the same example as before, but I can actually prove that it's non-permutative. So proposition, when Q is, I suppose I should label these, well, it always feels silly, it's my talk. When Q is 3 mod 4, P1 with 1 over X acting on it is non-permutative. Okay, so let's look at what's happening here. Suppose that we have well, I'm only going to look at the extension 2. So we're working over, which I might not have time. Let me list examples because I want to give more than one example. And then if I have some time, I'll go into the details of how you compute with this. We'll just call these examples. Okay, so now let's do something even more explicit because I think this example is quite nifty. So we're going to take the variety y squared is x cubed plus x, and we're going to work over f5. And I want to do this. This is not a phenomenon that's unique to f5. I just want to, this is a nice, very explicit example. And we're going to take the automorphism phi of xy. This is the automorphism of order 4. This is negative x iy. So in this case, I equals 2. We want the square root of negative 1, so it's 2. So then this x with phi acting on it is non-permutative. And the reason I want to give this example is that I want to make it clear that it's not, the next example is going to be more general, but it's also sort of going to be one-dimensional. I wanted to, well, genus 0, I suppose is what I meant. And I really want to make it clear that this is not like a genus 0 phenomenon. There's other more interesting things that are going on. And the last example I want to give is, so let's assume that Q is 1 mod 4, but Q is not equal to 1 mod 16. So this is Q is 9, or actually it doesn't matter. Q is not 1 mod 16. So then we can take P1 and now we can multiply. Again, we're multiplying by I. But now we're just multiplying by I, straightforward. We're just sort of stretching out. So then this is non-permutative. And in general, if Q is 1 mod 2 to the n, and Q is not equal to 1 mod 2 to the n plus 1, so you just have to pick this. What you want is you can take P1 and you can multiply by a, I'm going to mess this up. Yeah, you want an nth root of unity. Sorry, and it's not an nth, it's a 2 to the n plus first root of unity. And then this is non-permutative. And I'm out of time, so I'm not going to go into the details of, but it's really, right, it's really a fact. The reason that we were having trouble seeing it before is we were just working with this Z mod 2, and you needed you needed I to not be a square in order to be able to detect that as non-trivial. So in fact, these two propositions, the one in the middle with Q3 mod 4 and the one near the bottom, it's just a factor of needing I'm sorry, I'm blanking. It's just a factor of needing something which is not a square. When you have a square, you end up with a trivial internal coordinate because of various computational phenomena. But what you want is to be multiplying by something which is not a square. And that was what I want to tell you about.